Good afternoon, good morning, everyone. Today we're going to present a new series of our webinars. We're going to see how to obtain mesh independent results. This is Amal. I'm a technical support specialist of CFD in the EMEA region, and I have my colleagues here, Matt and Marwan. Hi, Matt. Hi, Marwan.
Hello.
Hey.
Hey. So by the end of this webinar, you're going to be able to find the slides as well as the files that we worked on of the models under this link that you see at the bottom. For today, we're going to discuss three main topics or three main parts, which are the meshing basics. In this first part, I'm going to remind you of the best practices and the basics to well mesh models. I'm going to talk in general. And then in the second part and the third part, it's Marwan and Matt. They're going to be talking about the mesh sensitivity study on how we help you get mesh independent results, where they're going to be explaining how to use the manual mesh, the manual mesh sensitivity study, and also the automatic meshing sensitivity, which is called also the mesh adaptation in Autodesk CFD. During this workflow, they're going to be explaining these process using example models like the exhaust manifold and the valve. So the basics of meshing. So mainly the mesh defines the model for the analysis. CFD takes the CAD geometry that you give it to it and then represent it with elements to process results of the analysis. Then in Autodesk CFD, use the automatic mesher, which chooses element sizes based on the CAD geometry. That means CFD looks at the curvature of your geometry and edge lengths of all the volumes. So CFD set tighter mesh elements over the heatsink, for example, on this model, over the capacitors to capture the high gradients of temperature due to heat generated by these components. How we can do it? We have some rules of thumb that we need to follow to get a well-refined mesh, to be able to say, now I have a good mesh that is able to capture curvature, geometry features like gaps, thin solid materials, and also regions of high gradients of velocity, temperature, and pressure. For example, as you see in this example, on the left side, it is a coarse mesh of the valve model, and this is a refined mesh. We can see here how the recirculation region with the coarse mesh is not well represented, and how refining the mesh helped better represent the recirculation area and the high gradients of velocity. Refining the mesh allows us also to refine the curvature of the geometry. Like in here, you can see that this is a bit coarse on this region, and here we can get a well-rounded edge.
Can I add something here? This is Marwan.
Sure.
Yeah, these are four interesting pictures that you are showing here, because in the first one, the valve, obviously the mesh actually captures the geometry pretty good, but it doesn't really capture the physics as much. In the pipe model down there, you can see that the mesh is so coarse that it doesn't even capture the geometry. Your circular tube is not even circular. So the mesh has to do things. It has to accurately represent your geometry, and it also has to accurately represent the physics. Visually, you can tell right away if it's actually capturing the geometry. So right there, you can say, well, that's not a good mesh. I need to refine it. I'm not even getting my circular shapes. I mean, you're never going to get a perfectly 100% circular, but it's going to be very close to it. And once you run it once you capture the geometry, I mean, really, if you're not capturing the geometry, you might as well not run the model. But once you capture the geometry and run the model, you might want to do, the refinement of the mesh to really see if you're actually capturing the physics of what is going on. At the end of the day, yeah, at the end of the day, as far as the geometry, your mesh is your model, not your CAD model. Once you mesh it, your actual model is the mesh. It doesn't matter if it was a circle that was converted to a six-sided polygon. That's what you have. You might as well have modeled a six-sided polygon in your CAD model to begin with, if that's your mesh.
Yeah, it's a whole process, actually. It begins by the coarse mesh. You focus on curvature, the geometries, the geometry components, and goes further to the physical phenomena like recirculations or high gradients. This is a good input. Thanks, Marwan. I can add also here how the flow passage in here in this region and the coarse mesh, the high velocity gradients wasn't captured as in the image of on the right side of the refined mesh. Here's I said some examples of geometries where the mesh wasn't well represented. We have a tube where we applied a coarse mesh. As you can see, how the edges or the cylinders are not well represented by the mesh. We need really to make sure that we have between or more than 6 nodes around the circumference of the cylinders. Another thing that we need to take into account is to refine the tiny solid or fluid volumes in a way that we get more than 6 nodes across the thickness. For example, we have here an example of a heat exchanger component, and then this is the part of air circulating around it. You can see here how the elements are big, either inside the solid or in the fluids volume, and how refining the mesh would help us better capture heat transfer between air and the heat exchanger. So probably you're asking how we can do it in Autodesk CFD. It's by using the meshing controls, where you can choose either a volume or surface or edge, and then refine it using the size adjustment. So it depends on your needs. If you're interested in saying, okay, I want to refine this volume, so you need just to select the volume and refine it. Or you say, I'm running, for example, free surface analysis, and I want to make sure that the free surface is well refined. So you need just to switch to surface and then adjust the size of the mesh element over the surface. Another approach is to split the CAD into volumes. For example, in the bullet model tutorial, we have here air, and this is air material, and here's the bullet material. We have divided the air volume into 2 parts because we want to make this inner part with finer mesh than the external air volume to well capture the high velocity gradients around the bullet. You have another option in Autodesk CFD. So splitting the CAD into volumes, you can do it in the CAD software, or you can use in Autodesk CFD the mesh refinement region in order to refine locations or regions of interest of your mesh without needing to go back to the CAD software. But sometimes you have thin solid parts where you need to thin solid. When I say thin solid parts, that means in a way that you have a thickness of 2 millimeters. In this way, I would recommend to split the thickness into 2 parts so that you make sure that you have at least 1 node through the thickness.
Hey, Amal, just a few notes here. Splitting the CAD's great when you still want an automatic mesh, which means it's just not uniform, but you in general need to enhance and tighten up the mesh. So this is used all the time on airfoils, and there's old webinars of people doing airfoils. They'll have 3, 4, 5 catted volumes around the airfoil, and I used one recently. I kind of used a diamond underneath an internal fan that was blowing air down into a huge kind of garage area. I didn't necessarily need it to be uniform because that would have been way too much mesh, but I did want to tighten it up so I could see basically the fusion of air and capture that. But the problem in CFD I was facing was that the elements were so coarse because it was this huge open garage that didn't have any CAD below, And again, it's based off of edge lengths and distance to other geometries. So sometimes it can get a little too coarse. So I love CADing that stuff, and refinement regions are awesome too. So
yeah, this is a good point. Thanks, Matt. Okay, so the basics of meshing are really related to the accuracy of your results. You start your first analysis by a coarse mesh that gives you an idea on the regions where you need to refine it. As Marwan mentioned, you start by saying, oh, my geometry is not well represented, so I need to refine it. And then you figure out that you have some flow regions or temperature profiles that follow the mesh scheme or the mesh elements, where you say, okay, here I need to further refine my mesh because probably I'm not capturing well the gradients in this region. So then as you go to final analysis and you need to match experimental results, you would need to refine the mesh and have tighter mesh elements to capture high gradients, as we mentioned. So obviously, as the mesh size goes up, the time it takes to compute this, since the complexity is increasing, is also going to increase as well. But at the same time, you're increasing the accuracy of your results in a way that you're matching the experimental data. There is a lot to talk about meshing and how it is important to match or to validate the results. I would recommend that you go into details on how to well refine the mesh or to better mesh your model by visiting or watching our previous webinars. Here's the list where you can access the different webinars that we've been presenting in the past, or visit our wiki page. So these webinars, I recommend seeing them because you can also see how we were able to present how to troubleshoot some errors that you meet or that you face when meshing your model.
I have a couple notes here.
Yeah, sure.
If that's fine. There's obviously a lot to go over here, so we decided let's touch on some basics of meshing, but really just focus on getting independent results. We couldn't do both in less than an hour, so that's kind of what we're getting at here.
Yeah, especially that in these previous webinars, there's a lot of content to see in there. We don't have to repeat everything from the beginning, and it's better to talk about new topics.
Yeah, I watched them when I onboarded a while back and really relied on them.
Exactly.
Another note about the meshing basics is, we showed a linear graph, but eventually it will go, non-linear, and you'll just be spending more time on solve. Your results will not be getting any better. So that's kind of the trick. I generally say, the best mesh is the coarsest one that gives good results, because, time is important. So, figuring that out and figuring out where that point is the goal of today's webinar.
True.
All right, Paul.
Okay, so I will hand the presentation to you. Okay, Let's see how we study mesh and get independent results. Okay, I'll give you the control.
Yep, just give me 1 second. All right, I think you can see my screen. Yep. I'm good, right?
Yeah, I can see it.
All right. So a mesh sensitivity study is just changing your mesh and trying to figure out where's the point where your results aren't really changing, and you can call your results true and good. You know, your results are always going to change a little bit. So I said, mesh independence is when your results marginally vary when a finer mesh is applied. And when I say change mesh, I pretty much just mean refine. You can always coarse and things will change. So, when you have geometry and hit auto mesh and run, it's probably too coarse, chances are. And it really depends on the granularity and the quality you need too. Different applications are going to have different mesh requirements. If I'm trying to do a verification study or try to match experimental data of a pump or something, I'm going to have to put more effort and time into it. And just one note, intermediate users, people using the software a while, definitely the support folks will be able to identify an area which needs more mesh based on the results. So I can look at a plane, if you can see elements, you can see gradients across there, it's definitely a problem. Kind of the rule of thumb we use here is results that change less or equal to 5% with a 30% increase in mesh is considered to be an independent. So we compound our meshes at 30%. That's kind of what we teach people. And 5% is, definitely what I consider pretty tight for CFD. It really comes down to what your own criteria is. Okay. All right. So a lot of times people ask me, what should I measure? What's my physical recording that I'm going to use as a reference? And that's really is based on what you're doing. It's a good way to phrase the question is, why are you running the simulation? If it's an electronics package, find the hottest chip or the one with the highest heat load on it. If you're looking at pressure across a pump, that's in your defining flow. That's what you care about, or vice versa. Heat exchangers, and a lot of these things are going to be pressure, usually not velocity, but that's what I would focus on anyway. And how do you measure these? I use bulk calculator with planes. That's what I did my example on. And you could use points, you could use monitor points, really there's a bunch of post-processing tools you can use there to sample results. All right, so there's two different approaches here you can take, and it'll vary based on your own preference, really. A manual mesh sensitivity is when you define your own mesh, and I don't want to get this confused with manual meshing. It just means you test results on your own. You basically set up an initial mesh, and you shouldn't just auto size. Put in the time to make this thing look as good as you think is necessary and as dense as you think is necessary. I don't really like clicking and generating meshes for some reason, so I just run for 0 iterations from 0 every time to generate a mesh. Just kind of a preference. And I wish more people would focus on this. I should have bolded it. Don't even bother running for any iterations and number, whatever, to convergence. Do not bother until you're confident in the mesh quality. It's really like step 1 or step 0. If that's not good, then everything else is a waste of time. So So when you have a mesh that you think is good, run until convergence, the initial one, record your reference values. So what I was doing was looking at pressure across, average pressure across the cut plane. Basically, you clone it, you go into meshing again, grab all the volumes, use the slider bar to go down to 0.7, which is 30% denser mesh, apply changes, and then you run from 0. Don't run from the last set of results or anything. You want a new fresh start from 0. And then record those values and basically repeat until you're happy and know what you're looking at is good. People really get caught up on knowing if my results are good, but doing this process on your own enough times will really make you confident in your simulation skills. All right, this is another workflow we have is mesh adaptation, which basically does this process for you. It's really similar and really easy. If you're kind of new, this could definitely help you. One thing you can do is start to compare how the mesh adaptation worked and compare it to your own workflow. I found some pretty cool things when I did this in preparation. Basically, you take your first mesh and run for 200, 400 iterations. You don't have to go to convergence. It's kind of up to you, but generally speaking, that's not the best practices. And then usually 3 cycles is sufficient. If you think you have a perfect mesh, you can just run for 1. And what's really cool is you're going to get this output data that tells you as a percentage how independent your mesh is, how your results are. So you can save cycles, which I always do because I'm kind of curious what's going on behind the scenes between mine and the final mesh. And then there's also an option to allow coarsening. So maybe you overmesh some areas. CFD is a time-consuming process, so why not allow coarsening where it could be done without sacrificing results? Here's just kind of the UI. It's really quite easy, but run until you have a set of results that are pretty good, a few hundred iterations on your mesh 0, basically, your version. Go to the adaptation tab, enable adaptation. Again, cycles to run is really up to you, but you're going to have a scenario and for every single one of those. So it gets time consuming pretty quickly. And then save cycles is completely up to you. It's merely your choice. And then you basically hit solve. So in the output bar, which is this image in the middle of the screen, you'll get a reading that says mesh independence. And I pulled this from mine. It said pressure 99 on change and velocity as well. So sometimes if you have a really coarse mesh, you might run 3 cycles of adaptation and you look down and it says 70-something%. That means you still have a lot of work to do. And just because you ran it, it's telling you there's problems. So anyway, that is there. When your project is done and you look in the output bar, that's for the last cycle. You can scroll up and see the data for the intermediate cycles, but what's at the very bottom there is always for the last one. All right, so I did a V8 exhaust manifold that I pulled off a GrabCAD. I basically, on the inlet side, basically where the exhaust gas would go from the cylinders, I had a flow rate. I just did a quick hand calc based on displacement and engine RPM and set all those, and then a 0 pressure on the outlet. One thing I want to note is the geometry, I wouldn't consider, simulation ready, but I knew from the beginning I was going to suppress it. So all I care about is basically the air volumes there. So I don't care about those bolt holes or whatever. It's all going to be suppressed anyway. And I didn't do any heat transfer. It's not really the point here. That would probably be transient. It's not really the focus. So I did a manual mesh sensitivity study. On the left was my mesh 1. I actually didn't take the best route here. Basically, I only auto meshed this, which I really should have just hit auto mesh and then enhanced it. Anyway, all it ends up making me do is have more scenarios and more tests. I ended up doing 5. Usually you can do less. It's just that my baseline was really coarse. And then I dropped in a cut plane, used bulk calculator, and I'm looking at pressure. So if I was, of course, if I was a design engineer, I would basically want uniform outlet pressure on all these pipes. But of course, the one farthest from the exhaust is going to have the highest pressure. Closest to the exhaust is going to have lowest. So, balancing there is really important. And that would be an end goal here. So again, this is my coarse auto mesh on the left. Just the process of tightening up the mesh is grab the volume. You can click and kind of grab everything by drawing a rectangle on the screen, and then you hit edit and use the size adjustment, slide it down or type in 0.7, and then always make sure to hit apply changes. For a while I was just using the enter key and that gave me some problems, so hit apply changes and then apply at the bottom, and you're good to go. So here's some of my results. And again, I did 5. Usually you can get away with doing like 3. It's just that my first is way too coarse. I guess the important thing is that, between mesh 4 and 5, there's really small changes, almost nothing, which gave me really high confidence that my results were mesh independent. What's cool is if you look between, the results between mesh 1 and mesh 5, they're all over the place. They look like, a third off at maybe more times, closer to 100% off. So I thought that was, pretty awesome, pretty interesting, and really valuable. All right, so now Marwan's going to show us his example, and then at the end we can jump into CFD and show us some, live stuff. So, all right, Marwan, I'm going to try to hand this off to you.
All right. Let me. Let's do that. Let me know if I can see my screen.
Yeah, we can see CFD.
All right, so let me bring up the PowerPoint here. So again, this is a model, and much like what Matt did, I changed the mesh manually. I still use automatic mesh, but I, went in and purposefully changed the mesh size by myself, and I also added a mesh refinement region. So just to kind of recap on the whole mesh convergence, it's something that any FEA analysis has to go through, not just CFD, stresses or anything like that. Whenever you do FEA, you're going to do a mesh convergence study. And if you ever contact tech support, we don't usually talk about that unless you're not getting the right results. If you contact us and say, hey, my model is crashing, let's say, or something like that, we're going to do what it takes to get the model running. And once we do that, we hand it off to the user. And it's their responsibility to make sure that they do have a converged mesh. We get them to the point where they have a running model, and we typically don't bring the topic up unless we start talking about the results. Yeah, my numbers are not making sense. Then we're going to start looking at the mesh, for instance. But by default, if the model is running and you're getting results and you're on your way basically with the model, your initial issue was dealt with, typically we're not going to be talking about mesh convergence. Not that it's not important, but it's taken really that the user, that's something they're going to do regardless. All right, having said that, my model here, go ahead.
You might just want to pop that in like presentation mode.
Oh, yeah. Here we go. Thanks, Matt.
Nice. Yep.
So this is the valve model. All the metal parts were suppressed, and only model the fluid, which is water in this case. We have volumetric flow rate of 25 GPM. zero pressure at the outlet, and those were suppressed, like I said, and it's only flow, no heat transfer. And the result that I'm going to be looking at is the pressure at the inlet. That is, of course, a result quantity that we will be looking at. So the mesh looks like this. Between my finest mesh and my coarsest default mesh, here's the difference. That's a cut plane here through the valve. So the valve is open 30 degrees, as you can see, and the inlet is on the left over here. Flow is going this way, and the outlet is here. And you can see there's quite a difference between the meshes and the two cases. So let me go to the model here. Where's my CFD here? Sorry, here's the model. So I have 4 cases. The first one is the default mesh, where I just went to mesh, auto size, and that's it. And I ran the model. Now, if you look at the geometry is represented pretty well. There's no fine detail in the geometry that I'm not going to be able to capture unless I have a fine mesh. However, if we look inside here, we can say right away, you can tell, well, that's really not so good to represent the flow here in this smaller gap. So right from the start, you might want to refine it. The second mesh that I used here, which I called finer mesh, all I did was grab the volume, go to mesh sizing, edit, grab this, and basically move the slider down and obtained a finer mesh. Clicked on apply changes, spread changes, and apply. And that gave me a little finer mesh, maybe a lot finer mesh actually. And this is this mesh here. Let's move the plane up a little bit. That's my mesh here. Obviously, I get more elements. I have a table here to compare the results. The next one here is using a refinement region. And the way this was done was to actually, here's something I would like to show you. What I did, all the materials here that were suppressed, I made a group for them. This way I can go down to the group, which is called solids down here, right click on it and hide it. That's an easy way to hide all these volumes that I'm not considering in my analysis. I went to mesh, region, and I defined this region of mesh refinement. By the way, it doesn't matter that the region is outside your model. It's not gonna do anything since you only have your part here. So the fact that the region is bigger doesn't really make a difference. But nonetheless, we have a refinement region here, and the resulting mesh looks like this. Let's go here to the plane, select the plane, edit, shaded with mesh, and that's what it looks like. So that's my refinement region, and obviously I can now better capture what goes on here in the narrow areas of my model. The last mesh was basically this same refinement region, but I refined the overall mesh altogether, as you can see in the PowerPoint presentation here. It's much finer. Now we can also go to the decision center here and look at the flow for each of those. And you can see that it better captures the flow as I refine my mesh. Now, if I look at the actual results, mesh 1, 2, 3, and 4. So mesh 1 is the default. Mesh 2 is just refining it by dragging the slider down. Mesh 3 has an added refinement region, and mesh 4 has that region and further refinement. Number of elements obviously went up quite a bit from 28,565 elements to 140,000 to 1.3 million to 2.47 million. And if I look at the inlet pressure and bars, this is how it changes: 0.157, 0.222, 0.232, 0.243. The first change from mesh 1 to mesh 2 is 41%. After that, it changed 4% and 5%. So really, I got the most bang for my buck is with mesh 2. If I didn't do the other three, the improvement is maybe all I need right here. After that, it's incremental. Of course, on such a small model, it doesn't really hurt you to do that, but on a big model, it might take way longer to go from almost 10 times the number of elements. So that could cost you a lot in time, and it's not going to give you too much advantage. Whereas, of course, here, this one gave us the most change in the inlet pressure. So obviously, going with the default mesh would not have been a good thing to do. And the numbers basically tell it all. That's all I had for this example. If you guys have any questions, please feel free to type them in the question.
Marwan, I can share mine, although it's really nothing new, but I can show mine if you want.
Sure. Hold on. Make you the presenter. Go ahead.
Mm-hmm.
All right.
Cool. So, I guess just a general workflow thing. When I did my original mesh, independent study, I kind of did my own here. 1, 2, whatever, and then I cloned the design, and I didn't take my auto mesh because you don't want the coarsest thing. So I took an intermediate version, mesh version, cloned just that scenario, dropped it down here, and then enabled mesh adaptation. So again,
that's a good point, Matt. You want to have a good starting point. You don't want to have a really coarse mesh and start with that for your mesh adaptation. You want to have a decent mesh to begin with.
Right. So this is showing pressure, but I mean, the end goal here, what was kind of cool is it'd be awesome if all these had the same pressure. Of course, this is a great representation. They're very different. You can see this is, way too coarse. I mean, 3 elements across 4, I've seen worse, but in something like this where you're not sacrificing much for a lot better, and we consider this, critical areas, you definitely want to add more. Now, and again, you can always look at the status file and look at how big your model is. So this is 35,000 elements. And my last one, I think, is huge. I think it's over 1 million. Let's check it out here. All right. Yeah, pretty tight.
Might be an overkill here.
Yeah. So be it. One thing. Let's check how many elements are here. 6 million, I think. 159. Yeah, this is too much. But anyway, I think I set these up before I really saw the results. So I ran them all, but you know, you'll see your results probably aren't going to be changing my last 3 scenarios. And again, this doesn't quite match what I put in the PowerPoint because I have more scenarios here. Now, what was really cool was, although I don't jump to mesh adaptation every time, I kind of like doing things my own way. The mesh adaptation got mesh independent results in like 730,000 elements, which is kind of embarrassing. They almost they have me by like a factor 10 there, almost. So because, you know, I could take this one, for example, and allow coarsening, and it's basically just going to coarsen it up and give me a much better mesh. It's going to save us time, which is pretty neat. I'm always interested in what that tool is going to do compared to what I do. I only have 1 volume here, so I'm adding mesh to areas that don't really need it. And that's something that mesh adaptation will not do. It's only going to add mesh in regions where it sees really high gradients across elements, which is pretty neat. In case anyone's, you know, wants to see the UI a little bit more, adaptation tab, I always allow, you know, save cycles and allow coarsening. There's additional parameters. For instance, Y plus adaptation is pretty cool. If you're using the K omega turbulence model and want to hit a criteria, you can set that, which is really neat because that can be very hard to hit at times. So I think that's all. Just one thing I will note is that you have to, you know, decide what convergence is. Sometimes you can get stuck in this really weird situation where you can't really find an independent mesh or you know, result independent mesh. And sometimes it helps to tighten the convergence criteria to tight, because these might be kicking out at different times and you're not really sure how solid it is. So if you're stuck, if you feel like your back's against the wall, like nothing's making sense, I would run these till tight and then basically test that, because that's going to cut out another source of some uncertainty. So yeah, that's kind of all I have to share there. Just give me 1 second here. Yeah, so we'll take any questions. Awesome. So we'll take any questions. Try to answer.
So Matt, we have a question here where the attendee mentioned that one of you, when meshing a part, one of you clicked only on apply, and the second one, I can't remember if it was you or Marwan, clicked on apply and sprayed changes. So he's asking what's the difference between both of them.
Okay, so they're definitely very different. You know, apply is to just implement that change in sizing. What spread changes is going to do is basically transition. It's going to help with spacing and transition between really large elements and really small elements and make that better. You don't want to go from an element that has an edge length of 10 millimeters down to one that has 0.5 millimeters. It doesn't look good and it's difficult. So what that will do is, you know, really, it basically just spreads the sizing so that there's a more smooth, more
transition.
smooth.
Transition between the meshes of the volumes. Okay, so I'm looking at the questions that we're getting here.
Yeah, I'm having a graphics problem, so maybe if you could just read them.
There's a question here about, any comments on what's under development for meshing and or mesh adaptation. We typically don't present that in those webinars. We leave that to a separate presentation. Once they actually get implemented, we discuss what the new features are.
Yeah, I would be interested to hear what you're looking for. I mean, just because we use the tool all day, we can't help but think it's pretty good. But I'm always interested to hear, like, what are your pain points, or in terms of mesh adaptation, what else would you like to see? So
Yeah,
please
I recommend
follow up there.
Yeah, and the idea station, I just want to remind everyone to go to the forums and go to the idea station section of the forums and just present any improvement that you would like to see implemented in the software over there.
Yeah, and then everyone can vote up for this idea and then can be accepted to be investigated by development. So once an idea is accepted, it will be escalated and then taken into account for the next future versions of CFD. Okay, so let's see. We have a user asking here. He says that every time I try mesh adaptation with an external flow, like a CFD study of a winglet or a wing fuselage interface, I quickly end up with 30 million fluid elements. And this is a lot for the hardware.
Sure.
So he's asking if he's doing something wrong.
Do you want to go, or should I?
Yeah, actually, it depends on his first mesh, how he started, and if he turned on allow coarsening, because probably CFD is refining some regions where we don't have high gradients or where we don't need a very refined mesh. So this is from my side. Do you recommend something else, Matt or Marwan?
Yeah, I recommend something. I mean, I really like mesh adaptation, but you still have to be like a very critical thinker about what your end goal is and stuff. For an airfoil, so the challenge of meshing at times is you don't know where your critical areas are. If you're doing an airfoil, you already know that's what you care about. That's the single thing you want to focus on. There's nothing else in the model. So you can just go on that on your own. When you do like NACA airfoil verification studies, you really have to tune everything right. People use 5 or more catted air volumes, and put uniform meshes on it, and use a ton of boundary layer elements, over 10, and really drive the Y plus down. So mesh adaptation is an okay application for that, but I can see why the tool doesn't know exactly what to chase, and it's given a tough problem. I would probably focus a bit more on doing a manual study on your own.
Yeah, especially when it is a simple CAD model.
Right.
I usually have used the mesh adaptation when I had like complex model like wind load models, where I have a big building with many details in it, and where it is like time consuming to do a manual mesh sensitivity study, where you need to refine each volume of the building.
Mm-hmm.
Okay, cool. And the next question, is there a way to limit the final mesh count? What do you mean by this question?
Like a max number?
No, yeah, I don't think there is.
No.
I don't think so either.
Yeah.
You can limit it by RAM.
Yeah, that's a hard stop.
Yeah.
Next, does adaptive meshing look at convergence or just run for a set number of iterations? No, it does look at convergence. It's just like any other run. You know, you're going to have the maximum iterations, and it's going to work within that, and it's going to convert. If it converges within, let's say, the if you set that for 500, if it converges in 365, it's going to stop. It's just like any other run.
Yeah, you need to give a fair number of iterations where you're sure that your simulation is going to converge. This is very important because after that, the mesh adaptation is going to look at the values of pressure, velocity, the variables that under study. And if you you give just, for example, 50 iterations, so the simulation didn't converge, you're going to have like more. The adaptive meshing wouldn't be efficient because it's not treating the converged solution.
That's right.
Okay. So next question.
Is there a way to end up with the best mesh with a constrained upper limit to the element count? Well, since there is no upper limit that you can set in the software, if you want to keep, if you set a limit for yourself, saying, okay, my hardware can't, manage more than 3 million or 4 million elements, then it becomes more of a user experience, your experience in getting the best mesh within that number. The way you use the software more so than the software is going to do it. Okay, now the other one. Sometimes when using the mesh adaptation, the solver will exit with an error. Any thoughts on the best practice? Well, if the solver is going to exit with an error, it's going to do it. It's not caused by the mesh adaptation. Something is causing it to exit with an error. Perhaps it can't mesh it for some reason. So if you go into that particular case and run it manually, or the scenario and run it manually, it's going to generate the same error, and you have to look at what's causing that error.
Yeah, we usually in this case recommend refining the mesh manually. This error can also happen when you are using a heatsink material, because the heatsink material creates a surface material in the background, which is not supported by the mesh adaptation routine.
Yeah. Another question here is, will the mesh adaptation also have the same effect if you're doing a thermal analysis? And the answer is yes. Not mesh adaptation, I'm sorry, mesh convergence. Mesh convergence really spans across all kinds of FEA analyses, be it heat transfer, fluid, mechanical stresses, all of that. It's an overarching concept.
Okay. So just to remind you that the PowerPoint file as well as the support files of CFD are going to be available under the link after we finish the webinar. Okay,